Simple harmonic motion we defined the other day as motion in which the restoring force is proportional to the displacement. We said yesterday that simple harmonic motion really is just Hooke's law. That's what we talked about back in the energy portion of our dynamics unit, F is equal to kx. And if you think about that definition again, where the restoring force is proportional to the displacement, this is it. As x gets bigger, F gets bigger. And that's different than every other force that we've dealt with up until now, or not including, of course, what we did back in the dynamics unit with Hooke's law. The force is usually constant. Doesn't matter how far I pull something, the force isn't changing. But in this case, as I pull it further away from the equilibrium position, the force gets bigger. Now, there's a small, subtle difference in what we dealt with back in Unit 2, in our dynamics unit, with what we're doing right now. Back in Unit 2, we talked about the applied force. How hard I pull on this spring or whatever is proportional to the displacement. The more I pull it, the harder I have to pull. The definition of simple harmonic motion isn't that the displacement affects the force that I pull with. Rather, the displacement affects that the spring pulls back with. In other words, the restoring force, pulling it back to its natural position, is proportional to the displacement. Now, how can we modify this equation to make it for the restoring force? The applied force is kx. The restoring force would technically be negative kx, because the restoring force is the exact same value as the applied force. I pull with 5 newtons to stretch it 3 centimeters. Well, the spring pulls back with 5 newtons. I pull it 10 newtons to pull it 6 centimeters. Well, the spring pulls back with 10 newtons. The restoring force will be the same value, but opposite direction to the applied force. So Hooke's law, in the context of simple harmonic motion, is usually F is equal to negative kx, but I wouldn't lose too much sleep over the negative. It's the same value. If you drop the negative there, I probably wouldn't mark that wrong. Okay? Motion in which the restoring force is proportional to the displacement. That's the technical definition. That's the real definition of simple harmonic motion. But we usually recognize simple harmonic motion not by an equation or not by values that we have to measure, but rather just by observation. We recognize simple harmonic motion by observing that something is undergoing repetitive motion, motion that repeats itself, back and forth motion. Like, for instance, a spring vibrating back and forth. That's repeating itself, and in that case, F is equal to negative kx. Like a pendulum swinging back and forth, back and forth. That's repetitive motion, and that's motion in which the restoring force is proportional to the displacement. Spent a little bit of time yesterday talking about the pendulum, and we kind of derived an equation for the period of the pendulum. We said it was T is equal to 2 pi square root L over G. We discovered yesterday that the period of the pendulum is dependent upon only 2 things: gravity, which we can't change, we can't control, and L, the length of the pendulum. It's not dependent upon mass, which we might think it does. It's not dependent upon the initial angle. That's a lie. Actually, it is dependent upon the initial angle. But when you're at small angles, the amount that it's dependent on it is small, so we don't pay any attention to that. At bigger angles, 50, 60, 70 degrees, it matters a lot more. Okay? When you go to the amusement park on Friday on your field trip, the swinging ship is going to go up to about 40 or 45 degrees. That's about the cutoff of that equation being valid. You wouldn't want to have it go much higher and still try to use that equation, because at that point, the approximation becomes not very good if you're above that angle. You can still use this for the swinging ship on Friday, but barely, okay, because the angle is getting to be a little bit too big. All right, we rearranged this yesterday as well. We solved for L, first of all. Let's do that again. What do we get rid of first if we want to solve for L? Yeah, good, 2 pi. How do we get rid of 2 pi? Good. T divided by 2 pi is equal to the square root L over G. What's next? Megan, what are you going to get rid of next? Good, square root. How are you going to get rid of that? Whoops, it's not square root, but what did you say it was? Square it, yeah. We're going to square this side as well, but when we square this side, the square root just disappears. What's next? We're getting close here. Dane, what's next if we want to get rid of, if we want to find L? Good, multiply it by G. So it becomes L is equal to G times T over 2 pi squared. Okay, done. If we're trying to solve for L. What if we're trying to solve for G? What if we're trying to solve for G? Yep. Yeah, looks kind of ugly, right? We take what we started with there. L is equal to G times T over 2 pi. And then we divide by the T over 2 pi squared. So G becomes L over T over 2 pi squared. Now, you guys saw a different form of that rearranged equation there in your textbook yesterday, I think. Okay, in the end, we said that you could square everything inside the brackets there. It becomes T squared over 4 pi squared. And then you could multiply by the reciprocal, which takes you to 4 pi squared L over T squared. But really, these two equations are the exact same thing. This looks a little bit neater, a little bit tidier, but in the end, I think this one's easier to get to. It doesn't really matter which one looks neater, as long as you can get that equation, right? You guys had 3 questions, I believe it was, that we were working on with this stuff on page 379. Were there any issues with those 3 questions on page 379? Any issues? Who got all of them? Good. Nobody had trouble with any of them? Okay, good, excellent. We finished off yesterday talking about resonance, and that's what we'll finish off today again as well, just reviewing resonance a little bit, show you a video, and then I'll leave you with a few questions here. In order to talk about resonance, we need to define a term first, resonant frequency. Does anybody remember what that means, resonant frequency? Yep, Mark? Yeah, the natural frequency at which something wants to vibrate. Everything wants to vibrate. Okay, everything has a natural frequency at which it will vibrate given the right conditions. Okay, yesterday I flicked the meter stick on the desk. It had a natural frequency and it vibrated at that natural frequency. It was consistent. Every time I flicked it, as long as I didn't change the length of the meter stick, it would vibrate at the same frequency. Pluck a guitar string. Unless you tighten it, or unless you put your finger on a fret, every time you pluck it, it's going to vibrate at the same frequency. It's resonant frequency. Okay, blow into any kind of wind instrument. Okay, now, unless you change the resonant frequency by putting your fingers on the, what do you call them? Band people, what do you call this? The things you put your fingers on? On a clarinet or something? Holes. All right. Unless you put your fingers on the holes on a clarinet or a flute or something and change the resonant frequency, then it's going to make the same sound every time. Even somebody's voice. Okay, think about that. Somebody's voice. What are you hearing? You're hearing the resonant frequency of my voice box. Why is the pitch of my voice changing? Because my muscles are changing the shape of the muscles in my throat, right? Everything's changing shape, which is changing the resonant frequency, which allows the sound that you hear, the resonant frequency that you hear, to be changing constantly. Okay, that's the varying pitch. Okay, blowing across the top of the water bottle, drink some water, changes pitch, because you've changed the resonant frequency, the natural frequency at which something will vibrate. Even the swing set. Okay, swing set back and forth, back and forth. Consistent, very predictable. But if you change the length of that swing set, then it's going to vibrate back and forth with a lower period, a smaller period. Everything has a natural frequency, a resonant frequency at which it wants to vibrate. Now, if I apply a force at the right rate, doesn't mean just push on something and expect it to go. It means push on something and push on something and push on something at a frequency that matches the resonant frequency, then a phenomenon called resonance occurs. Resonance occurs when the force is applied at the right frequency. In that case, the amplitude of the vibration increases. Now, it may increase to a certain point and then no further, or it may increase to the point where the thing breaks down. When you push on a swing set, back and forth at the right frequency, the disturbance grows, the amplitude grows, but only to a certain point. Right? You guys know that you push, look, I'm going higher. Look, Dad, I'm going higher. I'm higher and higher. But at some point, you don't go any higher. At some point, the amplitude of the vibration doesn't grow any bigger. But in some cases, as you apply that force at the right frequency, the amplitude grows to the point where whatever it is that's vibrating can't handle that vibration and it breaks. An example of that would be the opera singer breaking glass, right? You've got glass that has a resonant frequency. It wants to vibrate back and forth, and it does often. But when the opera singer, you hit the glass, right? You hit the glass, it's going to vibrate back and forth like this. But when the opera singer sings at that pitch for an extended period of time and loud, then she's going to cause the glass to vibrate and resonate. Not just vibrate, but resonate. The disturbance grows bigger because she keeps applying the force because the sound of her voice matches the frequency, the natural frequency of the glass. As the glass vibrates more and more, at some point, unlike the swing set that just doesn't grow any bigger, the glass actually can't handle the disturbance. The glass can't handle the amplitude. And what happens to it? It breaks. Right? The glass breaks because the opera singer has applied a force at the right frequency to cause it to break. How many people have ever walked across the pedestrian bridge in Okotoks? Probably everyone that lives in Okotoks, right? Who has walked across that bridge? Who has not walked across that bridge? The one behind the library. The pedestrian bridge in Okotoks, as you walk across it, sometimes you feel it kind of bouncing a little bit. So you try jumping up and down on it to try to make it bounce more. It's difficult to make it bounce more and more and more. You can feel that, like, intuitively, you don't have to know physics, not formal physics, to intuitively know that if I can jump up and down at the right rate, that I can cause this bridge to vibrate more with a higher amplitude, right? Intuitively, we know that. Kids know that. The problem with that, if you want to make it vibrate more and more, and this is my experience with that bridge anyways, is that the natural frequency of the bridge is too low. So as you jump up and down, you can't match the natural frequency. You jump up, you come back down, you're kind of in between cycles. You can't match the natural frequency by jumping up and down. And therefore, even though it moves a little bit and bounces, you don't really ever have to worry about it coming down, because it would be difficult, very difficult for a group of people to jump up and down and match the natural frequency and cause resonance occurring, right? It'll still vibrate at its natural frequency, but you're not going to cause the vibration to grow like resonance. Yep. A double bounce on a trampoline. Let me think about that for a second, actually. No, I think it would just be the opposite, actually, I think. When you're bouncing up and down on a trampoline, there's a certain resonance occurring with the, if you're coming up and down at the right rate, with the vibration of the springs that are around it in the, they call it the trampoline, whatever it is, the fabric, whatever that you're jumping on. And that ends up going up and down further and further. And if the person that's sitting on the trampoline will start bouncing up and down at the same rate, that I think you could call resonance. But when you double bounce somebody, you're kind of stopping, right? So you're kind of breaking that. So basically, you're stopping all of the energy in the trampoline, and the energy's got to go somewhere, right? So what happens to it? It ends up getting transferred to the little kid that's sitting beside you, and then that little kid ends up flying up into the air because he's got a lot more kinetic energy than he otherwise would. Okay, good question though. Does that make sense? going to show you a video here now of a bridge called the Tacoma Narrows Bridge. It was built in 1940, I believe it was. I was reading about this to get the exact date down. I think it was July of 1940. Even before this thing was finished, construction workers noticed it vibrating a lot, like moving in the wind a lot, more than you would think that it should. All bridges are going to move somewhat in the wind, but this was vibrating more than it should. In November, so July to November, August, September, November, 3 months after it was built, there's a gusty wind. It's not one gust of wind that took this thing down, but rather gust, gust, gust causes this bridge to vibrate more and more. When we match the resonant frequency of the bridge starts vibrating even more. Now it's not just resonant frequency, now it's resonance, because the disturbance is growing. The amplitude is growing. Now, the swing set can't grow far enough to break the swing set, but the bridge grew far enough to actually take down the bridge. I'm going to show you that video here now.